Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? Humankind is driven by curiosity. We want to advance deeper and deeper into space, fly to the end of our solar system and even beyond. But the space rocket is at the end of its development. Rockets might still take us to Mars, but if the universe is to be explored, totally new technologies are needed, and scientists are already working on them. Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. The launch of a Delta IV Heavy, the most modern rocket operated by American Space Agency NASA. With a thrust equivalent to around 50 million horsepower, it can take a payload of over 20 tons into orbit around the Earth. On this occasion, a new spacecraft, the Orion, was successfully launched into Earth orbit. NASA also plans to fly to Mars with this system. Even today, a rocket is still the only suitable means of transporting loads and people into orbit and beyond. Only with the help of a rocket can astronauts and supplies reach the International Space Station. Today, satellites determine our lives, but it is only with the power of rockets that they can be launched, or probes advance into space to explore asteroids and the planets in our solar system. Humankind's curiosity drives him on and on. We want to penetrate even deeper into the universe, to the boundaries of our solar system and beyond. But this calls for totally new propulsion systems, new technologies engineers and scientists are already working on.
Space, endless expanses. Humans have always wanted to know what these worlds look like, what dangers lurk there. And the means of transportation of choice has always been the rocket. But we don't want space travel to take years or even decades. Oh no, we want to reach every point of the universe within days or weeks perhaps. That has always been humankind's dream.
With present-day technology, even a mission to our planetary neighbors, Mars and Venus, would take months. A spaceship would have to travel for 40 years just to leave our solar system. Humankind wants to explore. We want to visit alien planets and travel to the edge of our galaxy. We want to fly through the universe and explore strange worlds like our ancestors once did as they sailed the oceans. But that means covering distances that exceed all imagination. So a quantum leap in propulsion technology is needed.
If we want to fly people into space, first and foremost, we need efficient propulsion systems that can accelerate spaceships up to speeds of 30 to 40,000 kilometers an hour. We can just about achieve that with current systems. But if we want to penetrate deep into the universe, to reach Jupiter or even leave our solar system, then we need speeds of 50 to 60,000 kilometers an hour. Those are the propulsion systems of the future.
Ever since the beginning of the space age, rockets have been the most important, indeed the only means of transportation. That is how Yuri Gagarin, the first man in space, left the Earth in 1961. It is also how astronauts were taken to the moon and brought back.
4, 3, 2, 1, 0.
Saturn V, the moon rocket from the 60s, is still the world's most powerful launch vehicle. The principle behind a rocket is 100 years old and has never changed. A cylinder is crammed with explosive material and the bottom end ignited.
I can see the entire Earth now on the center with
Those on the ground hope that everything will go according to plan. But the principle of the classic rocket has reached its limit. It is just about suitable for none too distant flights within our solar system. The endless expanses of the universe remain the realm of science fiction. With today's rocket propulsion systems, they remain out of reach.
At the moment, interstellar flights are the stuff of science fiction. In development terms, based on the current state of technology, we're talking about at least 100 years before any such project could seriously be embarked on.
Overcoming gravity, reaching Earth orbit, flying to the moon and back is no problem for our rockets. But they are too slow for exploring faraway galaxies.
Humans are also interested in flying to asteroids or other goals. There are simply no bounds to our curiosity.
It takes about 3 days to fly from the Earth to the moon. It will take an estimated 6 months to reach Mars, and 6 months to get back. That is the best our classic propulsion systems could manage.
The next goal, I think, will be to put people on Mars and just see what happens once they are there.
First to Mars, then to Venus, and after that to Jupiter. There is no shortage of destinations, even in our solar system.
Irrespective of where we fly to in space, the first phase of a flight is always the same. We have to lift off from Earth. And that always involves going straight upwards. Why straight upwards? Well, the atmosphere is about 100 kilometers thick. And if I'm traveling at a great speed, I don't want to experience any air resistance. So, straight upwards, and then into an orbit around Earth. Then I'm traveling at 8 kilometers per second, or 28,000 kilometers an hour. At that speed, the centrifugal force is just as great as the force of gravity pulling me inwards. By the way, this speed is also known as the first cosmic velocity. So I'm moving around the Earth at 8 kilometers per second. In this time, I perform what is known as a checkout. I check the systems to make sure everything is the way it should be. And only if everything is in order at this point do I perform a translunar injection burn. If I want to go to the moon, here's the burn. I need greater speed in the form of a second cosmic velocity. I leave the Earth's field of gravity and head for the moon. The region up to the moon is known as cislunar space. I could also fly to Jupiter. Then I would be in translunar space. I might even want to leave the solar system entirely, but then I would need an even greater velocity.
The current Soyuz carrier rocket looks little different from the rocket that once took Yuri Gagarin into Earth orbit. And even today, every launch of a space rocket still involves enormous technological effort and, above all, financial cost. The flight to the space station costs up to 150 million euros. And even today, every flight with a rocket is a major and also risky adventure.
You don't really believe it until the rocket actually lifts off. About 3.5 hours before the launch, you board this bus, which takes you to the launch pad. There you say goodbye to a small group of people. In my case, my father was also there. Then you're standing in front of this monster, which is hissing and snarling as if it were alive. The tanks are full of kerosene and liquid oxygen, and on the outside, clouds of vapor roll down as the moisture condenses in the cold air. Unlike in the US, in Russia, there's no countdown. You know in advance the precise minute and second when the rocket will lift off. Then the turbo pumps are activated. When the main engines are ignited, you feel a slight vibration. Then the rocket takes off.
Richtung Himmel.
At that moment, you know that it's really true. You're now on a journey into space. You're protected by a pressure suit. The suit's visors are closed. You actually hear the suit's ventilation more than anything else. But obviously you have radio contact with ground control. They give you regular information on how the flight is progressing. You keep a watch on the data from the life support system. If there were a leak somewhere, you would have to react immediately. Otherwise, you don't actually hear anything of the infernal noise in the capsule.
Lärm eigentlich in der Kapsel überhaupt nichts war.
In 1995, Thomas Reiter's first flight into space was to the Russian space station Mir. The journey took the three-man crew 2 days. Docking the Soyuz spaceship onto the Mir was precision work. Space station and capsule were hurtling around the Earth at 28,000 kilometers an hour at a height of around 400 kilometers. Soyuz has control thrusters and its own small rocket engine. Developed in the 1960s, it has hardly changed. Only the computers have become more modern, robust Russian technology.
We're talking about different philosophies. Most Russian rockets have liquid propulsion. Soyuz, for example, flies on kerosene and oxygen. This is comparatively old technology, which goes back to what was developed in Peenemünde during World War II.
And liftoff.
The Japanese use a combination of liquid hydrogen and oxygen as their core propulsion and solid fuel boosters. The same system in Europe, solid fuel boosters for the central thrust and liquid propulsion for the main stage and the upper stage, simply because the performance is better.
The combination of liquid fuel engines and solid fuel boosters was also used for the space shuttle. The space transporters were in service for 30 years. Then the program was shut down. The shuttle's last flight into space was in 2011.
At present, we travel through space with totally standard rocket technology, based in the final analysis on as much mass as possible being expelled downwards, with as high a speed as possible, and the rocket heading upwards into space. This is the kind of propulsion you think of when you build a rocket as a child. By and large, this form of propulsion has been maxed out. The chemical limit has already been reached.
NASA's new spaceship is also based on old concepts. The Orion is designed to replace the space shuttle and transport astronauts and freight into orbit. More than that, it is the space vehicle with which the Americans first want to return to the Moon, later fly to Mars. The spaceship is being built in cooperation with the European Space Agency, ESA. Orion can be equipped for different mission profiles and fitted with its own propulsion and supply modules. There is room on board for up to 6 astronauts. For missions to the Moon or Mars, the aim is for further modules to dock onto the capsule in Earth orbit, a spacecraft designed along modular construction lines.
Interface, the moment of truth for Orion for the next 9 minutes, 45 seconds.
In 2014, Orion took off on its first trial flight. Re-entry into the atmosphere was the acid test for the capsule's heat shield. These pictures remind us of the return of lunar capsules in the 60s and 70s. Just like capsules in those days after hurtling through the atmosphere, the Orion was first slowed down by parachutes and then splashed into the Pacific. The unmanned maiden flight was a success, an initial step in the direction of Mars. As with the Apollo capsules in the past, the task of recovering Orion in the ocean was handled by the US Navy. The launch vehicle for Orion is the Delta IV Heavy. After their moon rocket, it is the biggest launch vehicle ever built by the Americans.
We won't be able to reduce rocket size by very much. To get anywhere in space, we need big rockets. We will never fly into space with a mini rocket.
The engines can be optimized, but the principle always remains the same.
To fly into space, you need a lot of thrust. The more, the better. But what is thrust? And how does it work? A lot of people think thrust just isn't possible in space because thrust means pushing off against something. But in space, there is nothing to push off against, like a wall, for instance. So how does thrust work in space? Let's start with a simple example. Imagine I'm sitting in a small rowing boat. Each time I row, I push myself off against the water with my oars. This gives me thrust in the opposite direction. But what I push off against doesn't have to be solid or liquid. I can achieve the same effect by throwing something. If, for instance, I stand up and throw a stone over the back of the boat, I'm actually pushing off against the stone as I throw it. How great is the thrust in that case? That depends on the weight of the stone. The heavier the stone, the more powerful the thrust. The speed of the throw also matters. So speed and mass determine the backward force. And energy is not involved. It plays no role whatsoever. People think that thrust is energy. No, it's mass. As much mass as possible, as fast as possible. In this respect, thrust can come in totally different forms. Take a look at this. Here, a man is expelling a lot of water backwards at great speed. This generates counter-thrust, thrust upwards. That, too, is a principle behind a rocket. And we can go even further. Let's actually take a rocket. With a rocket, gas is hurled downwards. That is a lot of mass. You just don't see it because it's gaseous. But the rocket pushes off against this gas and is thrust upwards. So it's quite clear that this can also function in space. I shoot gas out backwards and can move in this direction. And if I want to travel in this direction, I again shoot it out backwards. That's the thrust principle in space.
The thrust principle can be applied not only for taking off and flying, but also for landing. Several private companies in America are working on this technology. The Falcon 9, built by the US company SpaceX, has already landed successfully after flights into space. And with the Falcon Heavy, SpaceX is already working on a bigger version. 3 propulsion stages will lift a payload of 53 tons into space. They could also transport 14 tons to Mars, because SpaceX is also thinking about the journey to our neighbor planet. When the payload has been deposited in space or the spacecraft released, the rockets return to Earth independently and can be reused. That is the plan. With this principle, SpaceX plans to dramatically lower the cost of transporting men and material into space, and thus develop a lucrative business.
If you look at, say, the cost of a Falcon 9 rocket, which is quite a big rocket, it's about 1 million pounds of thrust, and it is the lowest cost rocket in the world, and even so, it's about $50 to $60 million. But the cost of the fuel and oxygen and so forth is only about $200,000. So obviously, if we can reuse the rocket, say, 1,000 times, then that would make the capital cost of the rocket per launch only about $50,000.
With its reusable rockets, SpaceX plans to offer transport flights into space for less than $10 million. No other operator of satellite launches could compete.
Ground controllers here in Houston estimate the arrival to the capture point in just over.
In 2012, a SpaceX capsule docked onto the ISS. SpaceX operates its own aerospace center and now has 5,000 employees. And for the first time, a private enterprise flew freight to the space station. NASA supports SpaceX's plans. This is part of NASA's new orientation, which is for private aerospace companies to serve near-Earth space, while NASA works on new projects like a journey to Mars. Thus, SpaceX has signed lucrative contracts with NASA. Right from the start, both the carrier rocket and the capsule were designed for transporting people. In future, the Dragon spacecraft will also take astronauts to the ISS and bring them back to Earth. At present, this is only possible with the Russian Soyuz capsule. The Dragon is also designed to implement the company's philosophy of reusability. Dragon will not plummet into the ocean or land in the Russian steppe on parachutes. With the crew on board, the spacecraft will land independently at a spaceport and be able to fly back into space again. This is not wishful thinking. The reusable spacecraft is already in the test phase.
3, 2, 1, launch.
Technically, they will manage it, and manage it very well. As outsiders, however, we cannot really say whether it will prove economically viable. My view is that the ability of the Americans to develop commercial systems and to do business should not be underestimated.
In an emergency, the capsule could also land with the help of parachutes. The reusability of the capsule and its rockets means an enormous investment in technology.
It then has to be examined to see if anything has happened to it. I have to find out if it can be relaunched, or whether I need to build a new spacecraft. That would mean having the infrastructure for a new construction and possibly a repair infrastructure as well. I need people who can do that. But then I have to consider whether it's actually sensible. I've built a production line, so why not use that? Indeed, if you look at it, the Europeans do not reuse their boosters, and the Americans didn't do that with the shuttle either. So, we would say, it's not worth it.
What is certain, however, is that developments from private aerospace companies are giving the entire sector fresh impetus.
Where rockets are concerned, I think we need a new development. I'm not sure whether reusability is the ultimate solution. I really don't know. In fact, I would say it isn't.
The concept of reusability is not new. It is precisely why the American space shuttle program was conceived. A vehicle that would return to Earth independently after its flight into space. A repeatedly reusable transporter into the Earth's orbit. The shuttle program was a success, despite the huge costs involved and the loss of human life. A total of 14 astronauts were killed when NASA lost 2 of its shuttles through technical defects. Along with the space shuttle, the solid fuel rockets needed for the launch were also reused. After burnout, the 2 boosters separated from the space shuttle and drifted down on parachutes into the ocean, where a recovery vessel was waiting.
The thrust principle is eminently suitable for navigation in space because it enables you to pilot in all directions. But chemical propulsion systems have one major disadvantage. They're extremely inefficient. Isn't there anything better? Yes, there is. Electric propulsion. Let's take a look. You need a heavy gas, an inert gas, like xenon. At the end, that really goes whoosh. From the outside, the gas is forced into a chamber. Here, at the entrance to this chamber, the xenon atoms are ionized. That is what I'm drawing here. This plus sign in the middle of each atom indicates that they are positively ionized. The electrons, the negative electrical charge, are then drawn away laterally, and for the time being are waiting here, so to speak. So now we have these ions here. What we still need is acceleration. This is obtained with an electric voltage across the two plates you see here. You introduce a very high voltage, usually 10 or 20,000 volts. And when some of these ions reach these plates, they are accelerated to an extremely high speed. That's what I'm drawing here. At first, they are still positively charged. But they mustn't be, of course. When they are at the back, they have to be neutral again. How do we achieve this? The electrons that were drawn off here have to be reintroduced via what is called a neutralizer. It neutralizes the ions again, resulting in neutral xenon atoms. This neutralization, by the way, can be seen really well afterwards. Everything glows beautifully in a bluish-green color. And that's how it all works. Efficient means that the electrical output, which is pushed in here, is turned with great efficiency into a stream of gas. In other words, into thrust. However, the overall thrust is extremely small. The drawback, then, is that despite the high efficiency, since only gas atoms are involved, the thrust is not particularly great. The second drawback is that you need a vacuum chamber. In other words, the system would never function on Earth, only in space. But that's okay. Up there, astronauts would have enough time to operate it for months on end if need be.
Probes equipped with small ion engines have been flying through space for years. But NASA is also carrying out research into an engine that will make manned missions to remote destinations possible. In this respect, aerospace engineers and scientists are of course thinking of the journey to Mars. The propulsion system with its characteristic bluish light will, it is planned, also be used in satellites, enabling them to fly to the edge of our solar system, to Saturn or to Uranus.
It's the perfect form of propulsion for an unmanned probe weighing perhaps no more than a few hundred grams, or maybe 2 kilos.
But the force of gravity of the planets could also be utilized to fly through space.
The slingshot method is a totally different way of traveling through space. Let's take a look at how it works. First, we need a planet like this one. In our spacecraft, we fly very close to it. In other words, we shoot in here at a certain speed. Naturally, we are deflected from our course by the planet's field of gravity and come out in a different direction. So the flyby changes the direction in which we are traveling. But we can use this to put ourselves on another course. The other point is this. You'd think that I would leave the planet's field of gravity with the same speed at which I entered it. However, in the meantime, the planet has moved on. I'm pulled along with it on my flyby, and as a result, I gain speed. That's why this method has the name slingshot. I'm dragged along, and I'm traveling at a higher speed when I shoot out. With my flyby or a slingshot, I gain speed, but I can also change my direction. That's the trick. But there's more. When I fly on to the next planet and execute another slingshot maneuver, I gain even more speed. Then I fly on to the next planet and so on and so forth. Basically, I could slingshot my way from planet to planet and keep getting faster and faster. But there are limitations. Only once every 187 years are the outer planets in an alignment that would enable me to move from one to the other. The last time, by the way, was in the 1970s. The Voyager probe used the situation to be hurled into the depths of the universe. But the drawback is obvious. Once every 187 years is too seldom. We need a method which enables us to decide for ourselves where we're flying to. The best system, the best method, is nuclear propulsion.
NASA was already experimenting with nuclear propulsion in the 1950s. Promising prototypes were developed in secret laboratory tests. With the help of nuclear fission, the systems heated up hydrogen gas to a temperature of several thousand degrees Celsius. With a rapid exit velocity of 90 kilometers a second, they were clearly more efficient than chemical propulsion systems, but the development work was stopped.
It would simply be impossible to avoid releasing nuclear waste gases. Agreement was reached to stop nuclear weapons testing, and I cannot imagine an exception being made just for the spaceflight sector.
Some satellites have nuclear batteries on board, but research into nuclear propulsion for spacecraft has also recommenced.
The advantage of nuclear propulsion systems is that they have a very long service life. If you want to send a probe to Pluto, you need an engine that will function for 10 years.
Another concept is fusion propulsion, a literally inexhaustible source of energy. It would be ideal, but the concept is still in its infancy.
We don't know a lot about the materials we need. It can be done. But first of all, I would say that if we are going to use fusion reactors, we should first operate them on Earth to gain background experience. This would give us a solid knowledge base. And with 50 or 80 years of solid experience behind us, we could then consider whether it is possible to condense everything, to have a fusion reactor in the reduced size we would need for space propulsion.
The principle of packing the sun in a spacecraft and flying through the universe with it is mere wishful thinking.
Fusion propulsion simply hasn't been developed yet. We would first need to master nuclear fusion on Earth, and that has not been done anywhere. The idea is not totally inconceivable. It's just that from a current viewpoint, we are a long way from realizing it.
But what is unimaginable today could tomorrow already be standard. The future also brings technology with it.
Why not? Why shouldn't we suddenly have better technology available? Humankind has always come up with faster and better technologies. I'm hoping that will be the case here too. But we're talking about time leaps of many decades.
So, for the present, we are left with our tried and trusted rocket technology. It has taken humankind into Earth orbit and flown us to the moon. Perhaps it will also take us to Mars. Chemical propulsion is too weak for the really big step into space.
So what exactly is the situation with nuclear propulsion systems? From a physics point of view, they're perfect. They're extremely efficient and generate gigantic thrust, more than we could achieve today with any other propulsion system. As we know, however, they're ostracized. But fusion engines are not that bad at all, and they do not generate that much radioactivity. Besides, we could take off from Earth with chemical engines and only switch to nuclear propulsion in space. That would be the perfect combination, and I'd like to bet that that is exactly the way things will go.
But in order to discover strange new worlds, we would have to fly vast distances. The nearest galaxy to ours, Alpha Centauri, is 4.3 light years away, 40 billion kilometers.
To get there at all, I would need to travel at perhaps 1/10 of the speed of light. But even then, the journey would take 40 years. So it would be possible within the lifespan of a human being. But 1/10 of the speed of light is still enormously fast, of course. That's 30,000 kilometers a second. Present-day spaceships, if everything's going well, fly at 30 kilometers a second. So they are 1,000 times slower.
We can look deep into the universe. We can observe and explore our galaxy and discover new galaxies, solar systems, and also planets. But the distances between us and them defy all imagination.
Such dimensions make us realize how isolated we are here. We will need to make a massive effort if we are ever to leave our solar system to visit other worlds, which we're discovering now more often.
Man has been relegated to the role of observer. He can send probes to remote regions of the solar system and beyond. But for man himself, interstellar travel is inconceivable.
What exactly is interstellar space? To understand, we first need to determine what interplanetary space is. It's the region between the planets, in this case between the inner planets. Then there are the outer planets, Jupiter, Saturn, and so on. And on the very outside, where Neptune is, the last planet, is where interstellar space begins. In other words, the region between the stars. But the nearest star, Alpha Centauri, is a long way off, 4.3 light years away. 4.3 sounds like a small figure, but we are in fact talking about thousands of billions of kilometers. If we wanted to cover such distances with present-day engines, we'd be traveling for 100,000 or 200,000 years. What about electric propulsion, you might say? But we couldn't use that because electric propulsion systems need solar energy. And that's not available out there, so all that remains is nuclear power, fusion propulsion. But even that would give us no more than 1 or 2% of the speed of light. So it would still take a few hundred years to reach Alpha Centauri. That's a long time. But I believe that when the Sun or the Earth no longer exists, humans will take this step despite the many hundreds of years involved.
And so the journey to the boundaries of our solar system and beyond will remain a pipe dream that only the authors of science fiction books will be able to realize. In their imagination, they make use of totally different possibilities, like the famous concept of warp drive.
This is a form of propulsion which does not power the spacecraft itself, but shortens the space between my starting point and my destination. It bends space. So you could say that the spacecraft changes space. Put another way, the spacecraft itself doesn't move at all, like a surfer on an ocean wave. It's carried on a space-time wave. Theoretically, this is possible. The spacecraft is taken along by space, so to speak. But although this is theoretically possible, in practice, it will remain unattainable for us. That is because enormous amounts of energy would be needed, and not just a small atomic power station or a small fusion power plant. We can calculate that it would take 20 times the energy of our Sun.
The Sun itself could also provide thrust. The power of its eruptions and the solar wind they create could be used for sailing through the universe, the way explorers of the past sailed the oceans. And that is not just a dream. Scientists are working on the concept of the radiation pressure of sunlight being used for traveling in space. Models based on this system are already undergoing laboratory tests. The sail consists of wafer-thin foils that are extremely light. One problem is getting them to unfold in space without tearing.
Generally speaking, I'd be highly skeptical. To be in any way efficient, they would have to be extremely large. And they would have to weigh virtually nothing. They would need to be packed comparatively tightly on liftoff and then spread apart later. This calls for an extensive mechanism. And if the sails somehow started oscillating, there would be nothing with an attenuating effect, like air. A sail would go on oscillating. So the problem you would have is that the initial oscillation, which would never stop, would ultimately destroy it. For the sail to be really efficient, it would need to be the size of a football pitch or even larger. You would also need a foil which, for weight reasons, amongst other things, would have to be no more than a few micrometers thick.
And propulsion would, of course, only function near the Sun.
Today there are wafer-thin mylar foils that can be spread out to create areas of square kilometer size. In space, of course, there is no gravity, so the foils would remain stable. The only problem is that this concept has never been tried out, so we don't know how well it would work. Another problem is that sunlight, of course, diminishes the more you move away from the sun. So even if a solar sail were to function well here, close to Earth, the situation would look different next to Mars, Jupiter, or Saturn. And I don't even want to mention interstellar travel. So the idea isn't so good.
But perhaps the light for propulsion would not have to come from the sun at all. A further development of the solar sail, one which NASA is already researching, is photon propulsion. A spacecraft with a solar sail is fired into Earth orbit. From the Earth, powerful lasers then focus their light on the spacecraft.
Basically, a good aim would be needed. What's more, since the weather is often highly unstable, there would be temperature differences in the atmosphere and in its gaseous composition. Sometimes there would be rain and sometimes not, and sometimes there would be fog, all of which would be capable of deflecting the laser beam more or less substantially. The further out in space I was, the greater the problems I would have with the laser power reaching me. That's because along the atmosphere there is absorption, scatter, and beam expansion. The energy arriving at some time or other would be too little.
But according to NASA, a spacecraft with photon propulsion could fly from the Earth to Mars in 30 minutes.
So what's the deal with all these solar sails and laser sails? A solar sail needs a lot of sunlight in order to be accelerated, but this is only available within the range of the sun. Outside this range, a solar sail would be of no use at all. So a focused ray of light would be needed, a laser, hence a laser sail. But that would require a really big laser to be constantly focused on my sail from the Earth. But I would not like to be on board. Just imagine you're sitting in there and someone on Earth suddenly switches off the laser. Then you're stuck up there in space alone. Not exactly a happy thought. In the 1950s, a certain Mr. Buzzard came up with a great idea. Why take fuel along, he asked himself, when there's plenty in space in the form of ionized hydrogen? All I need, he said, is a grid system at the front of my spacecraft, which I can then charge with electricity. This will generate a magnetic field, and this magnetic field will suck ionized hydrogen atoms into a fusion chamber, where they will fuse and provide me with fantastic fusion propulsion. Sounds wonderful, but there's one huge problem: the fusion chamber. Why? Because pure hydrogen is extremely hard to fuse. I don't think we'll manage it in the next few thousand years. But it's at least possible, and that gives me confidence.
Anyone who travels through space must also be able to slow down their spacecraft as they approach their destination. This maneuver, too, consumes fuel, which has to be taken along just for that purpose. Consequently, engineers and astrophysicists are seeking new possibilities for braking maneuvers, and it is hoped that the natural magnetic fields of planets will help. A spacecraft with its own magnetic field could not only be slowed down in this way, but could also be propelled.
But is a propulsion system absolutely necessary? Is there no alternative? Yes, there is. Much has been written and talked about a space elevator. But what's involved? Let's assume that this is the Earth. All we need is a long cable that is anchored in the ground somewhere and extends far out to a counterweight. When the cable turns with the Earth, centrifugal force acting on the counterweight pulls the cable tight. The cable or tether would then be climbed. But how long would such a cable have to be? About 150,000 kilometers. Something that size would take some manufacturing. It would be enormous. Fortunately, there's a totally new form of technology available. Carbon nanotubes are very special materials that are extremely light and, above all, have great tensile strength. We can't make something like it yet, but if we could, such a cable would be no thicker than my little finger, and that over a length of more than 100,000 kilometers. A cable that thick and 150,000 kilometers in length would, of course, first need to be taken into space. We can't yet do that, but maybe we will in the future. From space, the cable would have to be lowered to the ground and anchored. And that would give us our space elevator. The question is, would it also function in the long term? And here some major problems arise, because there's plenty of space debris out there. Within a month, a piece of scrap would cut through the cable. And besides, it would be a real hindrance to satellites. There are 1,500 active satellites up there. At some point or other, one of them would hurtle into the cable. Not only would the cable be wrecked, so would the satellite. So in that respect, the system wouldn't work. But I still think the idea is good.
100 years ago, no one would have believed that humans would fly into space, set foot on the moon and operate a space station, let alone send probes to far-off planets. There are many ideas and concepts for totally new propulsion systems which will allow us to advance further into the universe. In future, perhaps humankind will even leave the solar system. There are no limits to the imagination. And it is in this light that the Space Elevator project also has to be seen. It is one idea for treading new paths.
A nice idea, but hard to implement. Someone would have to manufacture it.
Yet it is human imagination and ideas that have enabled us to fly into space.
Our universe is still full of mysteries. There could be some new effect that helps us, but at the moment, there isn't one in sight.
Our generation won't travel to strange stars, but future generations will.
Sadly, that's something I think that we won't experience, but such technologies will perhaps be available in 100 years' time.
Even though it is hard to imagine today, 100 years of developments will mean some fantastic discoveries.
To sum up, with present-day chemical propulsion systems, we could easily fly to Mars or Jupiter. Beyond that, we would have to hop from planet to planet with the help of the slingshot effect. But that means we would not be independent. To travel totally independently, we need extremely efficient and, above all, high-thrust propulsion systems. But all we have in this respect, and with regard to the future, is nuclear propulsion. And that, unfortunately, is ostracized. And even if we just wanted to leave our solar system, I don't believe there's any way around fusion propulsion. Whether warp drive will come is an open question. But even with fusion propulsion, we would still need hundreds of years to get to the next star. Whether humankind will manage that, I don't know, but it's possible.
Humans will develop old technologies further and find new ones. And we will advance deep into the universe in search of knowledge and also in search of ourselves.